Hello, and welcome to another wonderful day of energy balances. So, today we're going to be taking a lot of the basic concepts we developed last time with simple ways of how energy can enter or leave a system, pair them with simple enthalpies of reaction, and try and develop ways we can describe real kind of chemical systems. So, one of the important things to realize is most real industrial chemical systems are going to have chemical streams that are going to be composed of many different reactants or components. So they're going to be composed of, say, at least two different components, and they're going to be experiencing both temperature changes and phase changes, and maybe even a reaction change. So in these sort of cases, the heat going into and out of the system really needs to be calculated by finding the total change in the enthalpy, or how much the enthalpy change has the enthalpy itself has changed. So then in this case, the heat is going to be the same thing as the total enthalpy. Now, let's say I've got two components. Well, I've got to find the change in sensible heat for component one, the change in latent heat for that same component, and any reaction enthalpy for that component. And then the same thing for components 2, 3, and 4. So this can actually be quite a long process. And it turns out that this is going to be necessary for almost any chemical systems, especially with those where we've got where we have liquids that are going to very frequently be forced into the gas phase to increase the rate of reaction, because gases tend to move much quicker and be able to interact with catalysts and each other at a much more rapid rate, as well as having a greater kinetic energy, which can be used to overcome any reaction barriers. So let's go ahead and take a look at what this looks like kind of in the real world. So an example complex system might be, again, dealing with a mixture of ethanol and water. So let's say this is the mash from a fermenter, and I need to go ahead and pump it into a vaporizer to turn it into the gas phase. So I'm going to be vaporizing the whole mixture. So I'm starting at room temperature. I'm heating the whole mixture up to 110 degrees C, and I'm doing this at a rate of 10 kilograms per minute of this whole 9% weight mixture. And I'm going to use that to feed into a distillation apparatus. So I'm feeding it in as a hot distillation. So now here's going to be the question. What rate do I need to heat the system? So the rate's going to be largely driven by the rate of heat. But what I'm really going to need to do is split this into two major features. I'm going to need to find the enthalpy of the ethanol and the change in enthalpy of the water. Otherwise, it's going to take way more than a single slide. So let's go ahead and focus in on this ethanol part. So if I'm trying to figure out what the change in the enthalpy of the ethanol is, the first thing I'm going to need to do is figure out how much ethanol I have. So I have 10 kilograms of solution and a 9% ethanol solution, again, by mass. So when I do this, it turns out I get about 20 moles of ethanol. And then using this, now I have to split it up into the three major features. So the enthalpy of vaporization I provided is at the boiling point of 98.2 degrees C. So I have to figure out how much energy it's going to take to heat my 20 moles to this temperature with the corresponding heat capacity. And then I'm going to have the latent heat of the phase change. So again, this will just be the enthalpy of vaporization and the amount of substance. And then I'm going to end up adding in how much energy it takes to heat the substance from the boiling point to the ending temperature. So what we end up with is a little over 100 kilojoules to heat it to boiling, about 750 kilojoules to actually boil the ethanol, and then about 40 kilojoules to heat the vapor. So one of the big things you're going to notice is that it's very common for the latent heat to be the dominant part of any of these combined processes. And as a whole, we have a heat rate of heating of about 900 kilojoules per mole, kilojoules per hour. And again, most of this is going into the actual boiling of the ethanol. Now, we also need to repeat this whole same process for the water. So first thing we need to do is figure out how much water we have. Now, as it's a 91% solution of water, and water's a lot lighter, this is about 500 moles of water compared to 20 moles of ethanol. Guess who's going to be soaking up the energy? So similarly, we can split this process into how much energy it takes to heat the water, how much energy it takes to boil the water, and how much energy it takes to heat the steam. So you're going to notice that the dominant component here is absolutely going to be that vaporization of the water at about 20 megajoules, as opposed to about 3 megajoules and 0.1 megajoules for heating the water and the steam respectively. So turns out that I need to pump in about 23 megajoules of energy to get my steam to temperature and phase. So the total enthalpy change of the system, when I add in all the features, is only a little bit more than that for the water alone. So one of the things to note is that water is a real big sink of these systems. So the major contributor to the system, if you compare, is definitely going to be the water, and it's definitely the boiling of the water, constituting over 80% of the energy requirements, and thus at 80% of the costs. So this is often something that you'll find in reality, chemists trying to reduce how much of the water you end up heating, or trying to find some use later on for that heated water I generated. So one of the other things you should watch out for is that, again, a lot of enthalpies are going to be reported at standard state. And it turns out that's going to be kind of inconvenient for a lot of phase changes. So for example, let's go ahead and take a look at an industrial stream of chloroform, which has a boiling point of 91.2 degrees C. So I'm producing gas phase chloroform at 400 degrees C, and I'm going to cool it down to 40 degrees C. So now I want to figure out how much heat is this process going to give off, because I need to find some place for that energy to go. So again, big things I'm going to end up needing is the heat capacity of liquid and gas. And turns out now I'm actually in a little bit of trouble, because my enthalpy of vaporization isn't given at this 91.2, it's given at standard state of 25. So in this case, the solution is actually fairly straightforward, because the nice part about using enthalpy instead of heat is that it is a state function, meaning that it doesn't matter when the actual vaporization took place, as long as I know the initial and starting temps. So I'm going to actually send my calculation through an artificial system, as I'm going to figure out how much energy it would be given off by heating my gas all the way down to 25 degrees C. So again, using the heat capacity and the moles of gas. And then I'm going to assume that the chloroform condenses at room temperature, which it will not. And then again, how much energy it would take to heat it from 25 to 40 degrees C. So in this case, each of these individual components will not be reflective of what physically happened, but their overall function will still get me to the right point, indicating that my system's gonna lose about 2.7 megajoules of energy per minute as heat. So again, this helps show how we can take rather large, complex problems and kind of break them into subtler bits. So next time, we're going to start applying these approaches to a more combined system, where I have to account for real industrial systems as I start mixing in a little bit of mass balance. Till then, take care.